All right, morning, guys. Get started here. All right, any questions on 12.4, the circles? Seth sent me a message saying that I messed up on homework 12.3. There was a disagreement between my slides and what I had listed on Teams. So whatever you did for 12.3 will be fine. I sent him the corrections, but whatever you turned in for 12.3 will be fine. Obviously, that wasn't last night's homework. Last night's homework was 12.4. All right, this was on the circles. I especially liked question number 16. That was a good question. All right, no questions. Let's go over the answers here. So let's see. We start off with that table. This book just loves its tables. So questions 1 through 8 were all tables. There were two answers for each one of those. So here we go. Let's see. Number 1, the area, and it said it's leave. It didn't say this, but I did say this in the class. Leave everything in terms of pi. So if you actually multiply by 3.14, well, then it's not going to be the answers that I call out. And this is going to go for the test as well, too. Once we get to higher level math, which you are in right now, we generally always leave our answers in terms of pi. As you go higher level math, you'll understand why that's probably a good thing to do. If you're actually measuring something, like you got to cut some piece of metal or something like that, or do a calculation of area or volume, then you are going to want to, if you're dealing with circles, you are going to want to, or spheres, you are going to want to multiply by 3.14, the pi key on your calculator. Remember the pi key on your calculator, just so you know, it doesn't use 3.14, and it's not pi. It's still doing a rounding of pi, but it just simply has more digits. All right, with that out of the way, let's go over the answers. So on number 1, the area is 196 pi, and the volume is 1,372 pi over 3. 1,372 pi over 3. Really ugly answer. All right, number 2. Let's see. The area was 100 pi. That's a nice answer. And the volume was 500 pi over 3. Number 3, the area is just pi, and the volume is pi over 6. Let's see. Number 4, the area is 9k squared pi over 4. Now, if you put your k squared after the pi, and you 9 pi k squared over 4, that's fine as well, too. The volume is 9k cubed pi over 16. All right, number 5 was something you saw for a radius. The radius is 4. The volume is 256 pi over 3. Number 5, the radius is 9. The volume is 972 pi. Number 7, the area is 8 pi. The volume is 8 pi root 2 over 3. That one was an ugly one. Number 8, the radius is 6. The area is 144 pi. Number 9, 2 answers there, 4 and 8. So it should say the area of a sphere is multiplied by 4 and the volume is multiplied by 8. And that's because one of them is squared and one of them is cubed. All right. Number 10, same thing, 9 and 27. 9 and 27. Number 11, 1 centimeter. 1 centimeter. Number 12, 36 pi meters squared. Number 13, 21 pi centimeters squared. This was exactly like the one that we did in class, except they just threw in different numbers, 13 and 14. 14 is 15 pi centimeters squared. Uh, 15, the volume of the hemisphere would be equal to 4 times the volume of the sphere. And last one, my favorite question: could the ice cream melt, and would it melt into the cone, or would there be too much ice cream and it would overflow the cone? And the answer is no, it would overflow the cone. That ice cream would not fit inside the cone. The volume of the sphere is greater than the volume of the cone. Sounds like you're getting a pretty good deal if you bought that ice cream. Just not a good deal if you're eating it in the desert, though, I guess. You have to eat it quickly. Okay, that's it. Hey, I know I got to speak for this class. Let's not be lazy during this e-learning. Let's make sure that we're actually doing the homework, right? It'd be very easy for you simply to copy down the answers as I call them out and turn that in on Teams. Come on, let's not be lazy. Let's do the work. Let's put forth the effort. Do your job as a student. And then, by the way, obviously the challenges of e-learning are you don't get to immediately, unless you're doing this live, which, by the way, no one is live right now. It's just me in a room all by myself talking to the computer. Yes, I am complaining. I would like for you guys to show up live so that we can talk and you can ask questions live. But if you can't do that for whatever the reason, that's fine as well too. But please ask questions if there's something you don't understand. All right, today's actually a pretty easy day. This is what our schedule looks like. So we're on 12.5. We will do one chapter review tomorrow, and then we will take the chapter test on Friday. Obviously, since the new thing happened, hopefully you read the emails. You will absolutely positively be coming in and taking your PSAT on Wednesday. So you will be coming in on Wednesday to take your PSAT. Monday, I'm going to move that calendar to the left there. In other words, we're going to do 13.1 on Monday. You'll take your PSAT test on Monday. I meant Tuesday. Sorry. We're going to do 13.1 on Tuesday. You're going to take your PSAT test on Wednesday. No homework for that night. And then we'll jump in on Thursday, 13.2. There are 14 chapters in the book. We will get through chapter 13 for sure. Remember that third week that I'm showing right here, that would be the first week of May. The last week of May are your finals. The week before that, I teach usually up until Tuesday, and then we start on Wednesday with a semester final review. So really, there's basically 2 weeks here. So we're going to finish chapter 13 for sure. We'll take a chapter 13 test. I'll probably get into a couple sections of chapter 14, and then I'll run out of time. My goal here is always every single year to make it through chapter 12. I mean, I've got to make it through chapter 12. So we are ahead of the schedule. These extra chapters are kind of more bonus chapters than required chapters. So we are doing good for the year. Don't get lazy though. All right, here's your homework for tonight. And my fact checker, Seth, can make sure I keep straight on this. Seth has found a couple mistakes that I've made on Teams. One of them, I've been making it for a very, very, very long time. Now that's fixed. Okay, since there's no one live, and oh wait, I got someone live. Brianna's here. Yay. Thank you, Brianna. All right. I said today was easy. Let's see if I'm a liar or not. All right, here we go. Oh, by the way, it's on areas and volumes of similar solids. Similar solids. All right, I think it's a pretty easy day. I think you're going to find that as well, too. We just simply need to get through one table. It's a little bit of a painful table, but get through one table, and then you're going to see how easy this actually is. All right, some definitions to start off. So we've had similar polygons before, similar triangles, similar quadrilaterals. We have that before. But today we're doing something called similar solids. Well, as the name would imply, it's the same basic concept as similar polygons or similar triangles. It's just that it applies to 3 dimensions. So these are solids, fancy word for 3-dimension, solids that have the same shape but a different size. So we're talking about 2 cones that are exactly the same, except their sizes are different. Their sizes are different. So the relationship between their radius and their height is the same for both cones. They just simply have different sizes. You can imagine, I don't know, let's say the Eiffel Tower, a large one and a little model of it, right? Those would be similar solids. Same shape, just different sizes. All right. Yeah, that's it. That's literally the whole definition right there. We have done what we're about to do before. We did it with triangles mostly. We did it with other shapes, but mostly we did it with similar triangles. We won't get into all the I don't know, we got lots and lots and lots of theorems and postulates that we got from similar triangles. We're only gonna get one for similar solids. So let's gather some data. By the way, this is the proof of the theorem that we're about to show at the end here, and it's a crummy proof, and you'll see why here in a second. All right, so here are two. I'm going to claim that these two are similar, right? And that's why it's a crummy proof, because I'm claiming they're similar without proving that they're similar. All right, so I'm going to claim that those two cylinders are similar, and I'm going to claim that those two pyramids are similar. That's the start. Now, you can kind of see for the pyramid that they're similar. Check it out. It looks like everything from the small one is doubled into the larger one. So you double one side, you get 12. You double one slant height, you get 10. You double the height of the pyramid, you get 8. So that one's easy to see. The names of those two shapes right there, 1 and 2. So 1 is the large one, 2 is the small one. You'll see that's going to be important here in a second. For the cylinders, it's a little bit more flaky there, me claiming that they're similar. All right, so I mentioned we're going to do a table. So we're going to take this data and we're going to do a table. We're going to do a table with this data. So we're going to start off with the cylinders, and then the second column we'll do it the same exercise. We'll do it with the pyramids. All right, so let's see what we're doing here. So I have two cylinders, a large one and a small one. My claim is that they're similar. We have dimensions. Let's see, what dimensions do we need for cylinders? Well, we just need a radius and we need a height. That's the only dimensions we need for cylinders, radius and a height. I've got that. And it's asking me to fill in column number, well, it's column number 2 on the table. Column number 1 tells me what the rows should all be. So the first row says scale factor. So scale factor, if the two shapes are similar, remember I already claimed they were, if they're similar, you just pick two corresponding sides, any two corresponding sides, one from the big one and one from the small one. So I could pick the radius, right? It would be 6 and 4, or I could pick the height, 12 and 8. It doesn't matter which one I choose. So for instance, if I choose the height, and it says the scale factor, if I do 1 to 2, right, that would be 12 over 8. You see where I'm getting those numbers? I just pick one of the dimensions and its corresponding dimension on the other shape. So 12 was the height of the first cylinder, 8 is the height of the second cylinder. You know, like, why did I do 12 over 8? Could I have done 8 over 12? I could have, but if I look at my table, each one of those ratios says 1 over 2, 1 over 2. So I want the top, the numerator there to be a dimension off of the larger one. Could I have done 6 over 4? I could have. Check this out. 12 over 8 reduces to 3 over 2. If I had chosen, I didn't, if I had chosen to use the radius, that would have given me what, 6 over 4, and that also reduces to what, 3 over 2. So it doesn't matter which one I choose, I'm going to get the same value. Now, it would make a difference if I chose to go small to big. If I went from the small solid to the big solid, well, then it wouldn't be 3 over 2, it would have been 2 over 3. No big deal. All right, so my scale factor, we just calculated, is 3 over 2 if I go from 1 to 2. And notice that's what the column says to do, 1 to 2. The second one says I'm supposed to do base perimeter of the first shape over the base perimeter of the second shape. So this one's a slightly more complicated. Let's see, perimeter. Perimeter means the distance around. The base of a cylinder is a circle. So it's asking me to calculate for both shapes the perimeter of a circle. So let's see, perimeter of a circle. Do we have that formula? Yeah, we just simply don't call it perimeter. We call this perimeter of a circle the circumference. So I'm flipping through my book of truth, right? I'm trying to find that one theorem that talked about circumference, and we find it, and it says that circumference is equal to 2 times pi times the radius. So I need to do, let's see, I need to do shape number 1 first. So I'm doing shape number 1 first. I know that the perimeter is 2 pi r, and I'm looking at the shape number 1, and the radius is 6, right? So let's see, 6, if 2 pi r is the formula I need, then if I throw 6 in for the radius, I would get 2 pi times 6. And then we're supposed to make that a what? A ratio. And the ratio is the denominator is the base perimeter of of item number 2 or shape number 2. And shape number 2, once again, is another cylinder. And the radius of that is 4. So that would be 2 times pi times 4. So when I plug all those numbers into the fraction, that's what I get. Now we'll take a pause here, make sure we look at what we're doing. 2 pi r is the perimeter, or circumference. And we're supposed to do shape 1 over shape 2. I just did that. Now check out what happens. Look, a whole bunch of things cancel. Let's see, the 2's cancel, the pi's cancel, and you're just left with 6 over 4. Can you see why that cancels? Right? 2 divided by 2 is 1. I just didn't draw canceling. We'll do that now. And there we go. So those 2 cancel, and 6 over 4 reduces to 3 over 2. Now that's suspicious. Why? Because that was also the scale factor. Okay. All right. Well, that was kind of neat. All right. Let's continue on and plug that in. All right. So that's 3 over 2 as well, too. All right, now we get to the second one, and now we got to do some flipping through our book of truth because it says LA, and remember LA stands for lateral area. So lateral area of cylinders, we got to flip back a few pages and find the formula for lateral area. And once again, we're doing 1 over 2. Well, if you flip through the correct page, the lateral area, remember that's the curved surface, not the top and the bottom, just the curved surface, was 2 pi RH. That was the lateral area. That was one of the theorems that we wrote down, 2 pi RH. Okay, now I can handle this. Let's see, on the first one, the radius is 6 and the height is 12, but check it out. I'm making a fraction. I also need the bottom. That means the lateral area of shape number 2, and its radius is 4 and its height is 8. So I'm going to throw that in there. See where I'm getting those numbers from? 2 pi RH is the formula. The ratio is shape 1 over shape 2, and I'm just plugging in those numbers. As previously, look, a whole bunch of things canceled. The 2's cancel, the pi's cancel. We knew some cross canceling here. Let's see, 4 goes into 12, 3 times? 4 goes into 12 3 times. So the 4's cancel. 2 goes into 6, also 3 times. Why are you not writing, pen? 2 goes into 6 3 times. And 2 goes into 8, 4 times? So we get what? We get 3 times 3 is 9. We get 9 over 4. Hey, that's not 3 over 2, is it? Right? We got what? 9 over 4. If you didn't do any of that and you multiplied straight across, if you didn't do any, you still get 9 over 4. Now we're going to put our thinking caps on. We kind of thought we might get 3 over 2, but we didn't. But notice what we can do. I can write 9 and 4 differently if I choose to. I could write 9 suspiciously as 3 squared. I could write 4 as 2 squared, and look, I got a 3 over 2, just both things are squared, right? Well, why is that suspicious? Right, that's suspicious because notice in both scale factor and perimeters, right, we were calculating distances. Distances are measured in, so for instance, centimeters. But when we calculate area, LA, that's the A in LA, area, we calculate area, area is squared. And look, both numbers have been squared. So if the scale factor is 3 over 2, then anytime you calculate a distance, right, if the shapes are similar, you should get exactly the same number. And anytime you calculate area, whether it's lateral area or total area, you should get the same scale factor, just squared. And we did. Anybody want to make a prediction when we get down to volume? Bree, you think you know the answer when we calculate the ratio of their volumes? Oops, I didn't want to do that. All right, no prediction, Bree? Okay, so let's do the math then. Let's find out what happened. So volume of cylinders. We flip through the pages until we find the formula for volume of the cylinders. Volume of the cylinders was capital BH, except we said that was kind of a useless formula. So we did what? Pi r squared h. There's the formula for volume. We're gonna do that same procedure, right? We're gonna plug in the numbers for shape 1, radius and the height 6 and 12, and then plug in the formula for radius and height for shape number 2, and we get those numbers right there. All right, so after a whole bunch of canceling, right? After a whole bunch of canceling and cross reduction, canceling. Let's see, 4 goes into 8, what, 4 times? 4 goes into 12, 3 times. Let's see, 6 squared is 36. 4 squared is 16. Extend that fraction. So we got a 4 and a 16. Let's see, anything reduce here? Yeah, 4 goes into 36, what, 9 times? 3 and 16, nothing cancels. So we're good. 3 times 9 is 27. And the bottom number is 16. Well, we didn't get 3 over 2. We got 27 over 16. But check it out. 27 can be written as 3 to the 3rd power. And 16 can be written as, I'm sorry, we should have gotten an 8 here. Why am I getting a 4 times 2 is 16? I've got a mistake here somewhere. Let me back up. Let's see, 4 go. Oh, it's not a 4, it's a 2. That's our problem. Canceled wrong. 4 goes into 8 2 times. That's better. That's better. All right. We get what? 27, and what happened to my 16? I've made too much of a mess here. I'm gonna erase this. Let's do this cross reduction one more time. All right. Let's try this again. So what would this equal? 6 times 6 is 36. So I get a 36 times 12 all over 4 times 4 is 16 times 8. All right, much better. Now let's do some reducing. All right, let's see. Well, how do we want to do this? Let's go by 4s. I'll do this in a different color. Let's see. 4 goes into 16, what, 4 times? 4 goes into 12, 3 times. 4 goes into 8, 2 times. And 4 goes into 36, 9 times. There we go. Sometimes you just got to erase things, start over. That gives us what we thought we were going to get. 27, not over 16, but over 8. And that can be written as 3 to the 3rd power. 3 times 3 is 9, times another 3 is 27. And 8 can be written as 2 to the 3rd. 2 times 2 is 4, times another 2 is 8. And we get what we thought we were going to get. I'll make this nice and pretty now. Nice and pretty, we get 3 to the 3rd, 2 cubed. So what's the big thing about this? Well, look what we did. I said that we started off with similar solids. So once you establish the scale factor, pick any 2 corresponding sides. Well, then any measurement of distance, that means any side measurement, any perimeter measurement, is going to be exactly the same as the scale factor. And any measurement of area, be it lateral area or be it surface area, total area, will be the scale factor squared. And any measurement of volume will be the scale factor cubed. Okay? So that's our hypothesis. This is why it's a crummy proof. We're just doing it by using 2 examples. So let's see if it worked out for our pyramids. So our pyramids, step number 1 is we set up the scale factor. You pick any 2 corresponding sides. I'm not picking 2 sides on the large one. I'm picking 1 side and its corresponding side on the small one. So for instance, if I pick the slant height on the big one is 10. The slant height on the small one is 5. I could have picked 8 and 4 if I wanted to. Notice we get 2 to 1. So the scale factor is 2 to 1. If it follows the same pattern as the previous one, when we calculate the perimeters, we should also get 2 to 1. Let's see what happens. On the big one, the perimeter, these are square pyramids. On the big one, the perimeter, let's see, one side is 12. 4 times 12 is 48. I would get 48 over small one side is 6. 6 times 4 is 24. I would get 48 over 24, and that's 2 to 1. If it follows the same pattern, then the lateral area of the pyramid, I should get 2 squared over 1 squared. Right? Let's see if that happens. Flipping through our book of truth, the perimeter, the lateral area, remember that's the sides, those are those 4 triangles. They're added together. Remember the formula ended up being PL over 2. P is the perimeter, L is the slant height. So on the big one, let's see, PL, the perimeter was 48 times the slant height, which was 10, all divided by 2. On the small one, the perimeter was 24 times the slant height is 5, all over 2. A whole bunch of math here. Let's just go through it really quickly. The 2, oops, I didn't want to do that. The 2 and the 10 would reduce to a 5. The 2 and the 24 would reduce to a 12. Let's write again what we get. So I get 48 times 5. There's going to be some more canceling we can do. Over 12 times 5. The 5s would cancel, and you'd get 48 over 12, which would reduce. 12 goes into 12 once. 12 goes into 48 4 times. So we get 4 over 1, but we didn't want 4 over 1. We were expecting 2 squared over 1 squared, but check it out. That's what it says. 4 can be written as 2 squared. 1 can be written as 1 squared. Hey, we got what we expected. All right, let me erase all that scribble and write it nice and pretty now. We got what we expected, which was 2 squared over 1 squared. Last one we'll do is the volume. So let's see, the volume was, the base area times the height, all divided by 3. Remember, there was 3 of these that made one prism. So base area times the height divided by 3. The base area for the big one is, 12 times 12 is 144. So we get 144 times the height, not the slant height, but the height times 8. On the small one, 6 squared. 6 squared is 36 times 4. So we get all that mess right there. After, I'm going to cut to the chase here. After all that work, we get 8 over 1. After all that reduction, you're going to trust me on this one, we get 8 over 1, and 8 can be written as 2 to the 3rd, and 1 can be written as 1 to the 3rd, and we got what we expected. So to summarize for a final time, if you have 2 similar solids and you establish the scale factor, then any measurement or any comparison of the ratios of a distance of the 2 shapes will be the same number. Any comparisons of their areas will be the scale factor squared, and any comparison of the volume will be their scale factors cubed. Pretty convenient. You're going to see that tonight's homework is not very challenging, but we do need to write this down more formally, and this is theorem 1211. 1211 says 3 things. It says that if you know the scale factor of 2 similar solids, then the ratio of their perimeters is also the scale factor. The ratio of any area measurement of the 2 shapes will be the scale factor squared, and any measurement of their volumes will be the scale factor cubed. All right, I will pause so you can write this down. All right. So homework will look something like this. They will give you 2 shapes. They will either be similar or they won't be similar. If they're similar, then they must follow the steps that were outlined in the previous theorem. If they're not similar, obviously, then they won't. This one says calculate the ratio of similar solids. So they're claiming that they're similar And you're only given one dimension. You're given the base. So it says, calculate the ratio of the base perimeters, the lateral areas, and the volumes. This is ridiculously easy. You pick any two corresponding measurements. Well, we're only given one, so this one's a bit easier. So the one thing you will have to know is whether you want to go small to big or big to small. So let's say, for instance, I'm going from small to big. So small to big would be what, 6 to 10? 6 to 10. So the first one I'm going to do is their perimeters. All right. Well, we can either actually do the calculation of the perimeters, or we can follow theorem 1211. Well, 1211 says that if you know that their scale factor, well, then their perimeters is also the scale factor. So let's see. I know their scale factor, it's 6 to 10. Now that's not reduced, so we probably need to reduce that. 2 goes into 6, what, 3 times? So if the scale factor is 3 to 5, then that's the scale factor of their perimeters. I mean, you're literally done. That's it. Finished. And the cool thing now is the rest is really simple. Their lateral areas, I don't need to look at anything other than the scale factor. The scale factor was 3 to 5, or 3 over 5. So anything involving their area, whether it's total area or surface area, total area or lateral area, is going to be that scale factor 3 over 5 squared. So without doing any looking at the shape, I already know 3 to 5 was the scale factor. Well, then their lateral area has got to be 3 squared over 5 squared. Now the question is, should I leave it as 3 squared, 5 squared, or 9 over 25? So yes, you should actually now do that squaring. Obviously, the last one we're doing is the volume. So 1, 2, 3 just mean there's 3 answers here. And what, like I said, it's a pretty clear theorem. Simply take the scale factor for any volume measurement, cube it. So I simply cube it. 3 cubed, 3 times 3 times 3 is 27. 5 times 5 times 5 is 125, and you're done. Yes, homework is literally this simple. All right. To prove it to you, I'll use this page, but we'll look at some of the homework. Let's see, what did I assign you? I assigned you 1 through 11 all. Let's see if Bree woke up. Bree, you on live with me now?
Yes.
All right, pick one. 1 through 11, pick one.
10.
All right. Assuming that the higher the numbers go, the harder it should get, let's look at number 10. All right, this is 10 on page 511. This isn't classroom exercises, this is the homework. All right, number 10, it says the scale factor for a certain model freight train is 1 to 48. 1 to 48. That's the scale factor. If the model of a car of the train holds 90 cubic inches, so that's talking volume, holds 90 cubic inches of coal, what is the capacity in cubic feet of the actual hopper car? All right, so this one is slightly more challenging because it gives it to us in cubic inches. All right, so if you just do a direct, hey, all I got to do is the cube root, find everything, you know, we're going to run into some problems. So let's see what happens here. So 90 cubic inches, okay. If we leave it in inches to start with, we can, to get to our scale factor. Eventually, we're going to change it to feet. But let's do that at the very end here. Once we get to this scale factor in inches, we'll convert it to feet for the final one. So, okay, so let's see. We know that we are given that if this is the scale factor, we know that in feet, that would be 1 to 90, and this is in inches, right? And this would be 1 cubed, and this would be the cubed root, right, of 90, because I don't know what that is, but what number cubed is 90? But I do know that that is the start right there. So cubic inches. So the question is what the scale factor? Well, we got the scale factor, right? The scale factor is 1 to 48. So 1 to 48 is the scale factor. Okay, let's see what we do now. So we got to figure out the actual train. Now remember, this is your small and this is your big, right? So small was the model. Why are you not writing? Small was the model. And the big one was the real train, All right. We do know that the cubic inches of the model train would be 90. So in other words, what we're saying is that our new fraction, where does this go? Well, this goes on the top here, right? Let me erase this other part. Oops, erase you. So 90 cubic inches applies to the model train. We need to figure out what that would be for the real train. Okay, so what are we going to do here? What are we going to do? What we're going to do is notice it says there's a hint there. It says see exercise 10 on page 477. So whenever they give you little, I don't know, hints like this, don't assume that it's not a smart thing to actually just flip things around. So if we flip back to, and it's a classroom exercises, if we slip back to see exercise 10 on page 477, it gives us literally a conversion factor of how you're converting things from inches to feet or inches to yards or inches to, in this case, we want to know, is it in cubic feet? It gives us cubic inches. So let's see, what part of question 10, A, B, or C would refer to this? I have cubic feet. I'm trying to find a cubic inches here. It looks like B is the one that we're going to use. And we figured out that 1 cubic feet, this is the last part of C, we found out that 1 cubic foot is equal to 1,728 cubic inches. All right. 1,700 cubic inches, 1,728 to be more precise. Bree, we're going to punt on this one for a second because I'm doing a pretty bad job of explanation. I'm going to re-record this part of the video and I'm going to put a really good explanation for number 10. Pick another one, please.
Okay.
Because I have to explain. I can't just throw that out there. I got to explain why it's 1728.
5.
All right, number 5. It says, assume that the Earth and the Moon are smooth spheres with diameters of 1,200 or 12,800 kilometers and 3,200 respectively. Find the ratio of the following: lengths of their equators, areas, and volumes. Okay, so we have 2 similar spheres, the Earth and the Moon. That's why they said that assume that they're smooth, which they're not. Find the ratios of the following: lengths of their equators. So lengths would be what? Circumference, not an area. So basically, we just need to figure out scale factor. So there's an A, B, and a C. So let's do, does it say small to big or big to small? Assume the Earth, it doesn't say. I can see the answers here. They're doing big to small here. So we'll do big to small. And it wouldn't be wrong to do small to big. So if we do big to small, let's see what we're given. We're given that the 2 corresponding sides are, these are going to be really big numbers, 12,800. And these are diameters, 12,800. And the other one is 3,200. Okay, so all we have to do is reduce this to find out the scale factor. All right, the easiest way to reduce it is get rid of your zeros first. So we get 128 over 32. I'm going to assume that 4 goes into 128. It does. 4 goes into 12 3 times. 4 goes into 8, 2 times. 4 goes into 32 8 times. So I get 4 to 1. Okay, cool. So 4:1 or 4/1, that is your ratio of what lengths of their equators. Now, why can I say that? I never calculated the equator. Well, remember, equator would be a measurement of circumference. Circumference is a measurement of distance. And theorem 1211 says that anything dealing with distance, the scale factor is the ratio of their distances. Okay, so that's A is 4:1. So this is part A. And now we got a scale factor too. It's both a scale factor and a ratio of any of their corresponding distances. Part B says do their areas. All right, in this case, surface area is what they're talking about. Cool. So if the scale factor is 4:1, well, theorem 1211 says, well, you want to find anything with area, square top and bottom. So we square top and bottom and we get what? 16/1. That was quick. And then part C says their volumes. Theorem 1211 says take the scale factor and simply cube both the top and the bottom. So we cube top and the bottom. See, 4 times 4 is 16 times another 4 is 64. So we get 64/1. 64/1. And that's it. That's number 5. Most of the questions are like that. The only one that is a bit challenging are 9 and 10. I'll add to the video here after we stop right here, and I'll give you the explanation. Let me circle these for that explanation for number 10. All right, any more questions? All right, that's all I have for you today. That is all I have for you today. Try to stay motivated. Try to stay up on your work. We will continue onward. I did show you the calendar. Let me clear this stuff. I did show you the calendar just to reiterate. Remember, you're going to be taking that PSAT on next Wednesday. You have to bring in your graphing calculator. You have to bring in your graphing calculator for that day of the test. I got nothing else for you. You guys have a wonderful day, and I will see you guys in class tomorrow.